So here's an interesting problem we often see for circular motion. We have a car going around a bank curve. Here's a top view. The car is basically up here going along this track. And generally, when we have a flat road, and if I had a car over here, the force of friction supplies the centripetal force to keep this thing going in a circle. Well, the force of friction has a limit, which is basically mu s times Fn. And what we want to do in the case of a bank curve is you see that the centripetal acceleration is in that direction, so the normal force here contributes a small component towards the centripetal force, allowing a larger centripetal force and hence a larger velocity around the track. So I'm going to go ahead and erase this a little bit here. So I'm going to make a free body diagram for this car. What are all the forces that it feels? I'll kind of draw it right up here. We have the normal force acting perpendicular to the surface. Then we have the force of friction. As this car speeds up, the car wants to slide up this way. Friction has to keep it in line, so friction is acting in that direction. And so force of friction is acting in this direction here. And if this is my axis, then this angle here is theta, and this angle here is also theta. As you could see that this angle theta is an alternate interior angle to this angle theta here, because of this one here is the actual theta. This also is theta. And since this thing is rotated by that, makes this also theta. So if I were to look at the forces, and then finally I have the force of gravity, mg, acting down here. Now, as far as this plane is concerned, the sum of the forces have to be zero in the y direction because the car is not moving in the y direction at all. So if I were to see what other forces I have in the y direction, I have n times cosine theta, which is this component, I'll draw it in red, this component of the normal force, that's positive upwards, plus this component of the friction force is acting upwards as well, downwards. It's also in the y direction. So I guess instead of putting a plus sign here, I put a minus sign, minus the force of friction, which is acting in this direction. And so that would be force of friction times sine of theta. And so again, some of my up forces have to be equal to zero. And so here's my some of all my forces in the vertical direction have to be zero, excuse me. And so I have n cosine theta acting upwards. And then I have this acting downwards. And I also have gravity acting downwards. And the sum of all of these has to equal zero because I have no acceleration in that direction. So I can rewrite this as n cosine theta minus force of friction sine theta equals mg. Now let's look at the sum of the forces. This was the sum of the forces in the y direction. Sum of the forces in the x direction, I have this component of force of friction acting in this direction. So that is force of friction times cosine theta, plus I have this component of the normal force also acting in that direction, in the negative x direction, but I'm going to call these all positive because this is the positive centripetal force direction. So I'm going to stay in line with that and treat these as positive, as if they're positive. So again, the forces acting towards the left, add up all the forces acting towards the left, this component over here, these will all be, again, I could have drawn my thing on this side over here and then it would have been plus, but you get the idea that it really makes no difference. Um, it's just that the way I've drawn it here, x is in the left direction. So anyway, some of the forces in the x direction, we have this component of friction over here, plus this component of the normal force, which is n sine theta. These two are the two forces that are creating this net force, which is going to be the centripetal force, so this must equal to mv squared over r. So now we have two equations, one here for the y direction, and this one here that we derive from the forces in the x direction. And so now I could combine these two to solve for the maximum velocity v that I can have. Continuing on, looking at equation 1, I can rewrite that as n times cosine theta minus the force of friction, if you remember by definition, is mu times Fn, or mu times n, using n here. So then this right here becomes minus mu times n sine theta, and that's equal to mg. Looking at this guy here, I'm going to rewrite him. Force of friction again is mu times n cosine theta plus n sine theta is equal to mv squared over r. So now I'm going to go ahead and divide these two equations. I'll go ahead and divide equation 2 by equation 1. Okay, so I'm going to write mu and cosine theta plus n sine theta equals mv squared over r. And I'll divide both sides by this side, which would be n cosine theta minus mu and sine theta, and that's mg. And so now I can get these n's to all cancel away. I'm dividing up and down by n. And so what I'm left with is mu cosine theta plus sine theta, all divided by cosine theta minus mu sine theta is equal to mv squared over r divided by mg. M's cancel, leaving me with mu cosine theta plus sine theta all over cosine theta minus mu sine theta is equal to v squared over rg. I'm going to go ahead and erase this so we have some more room to work on. Okay, now I could rewrite this by, let's say, dividing upstairs and downstairs by sine of theta, or actually dividing upstairs and downstairs by cosine of theta. If I do that, this gives me mu plus tangent theta, because all I'm doing is dividing up everything upstairs by up here by sine theta, by cosine theta, so that cosine theta over cosine theta gives me a 1, which is just the mu, plus sine theta over cosine theta gives me tangent theta, all divided by, again, 1 minus mu, and divide this um, by cosine theta, again get a sine theta, mu, sorry, a tangent theta, I get mu tangent theta, and that is equal to v squared over rg. So then v would equal to rg times mu plus tangent theta, all divided by 1 minus mu tangent theta, square root. And so this would give you the maximum velocity that you can attain when you are moving with this angle of 22 degrees. That's your bank. Radius of curvature is 48 meters. That's from here to there. And so we plug everything in here. We know R is 48, G is 9.8, mu is 0.67, and theta is 22 degrees. So you could put that all in the calculator and solve for what your velocity is going to be. I can go ahead and do that on my calculator if you don't mind waiting a few minutes. This is just a whole bunch of things you got to put in. So let's see, 48 times 9.8 multiplied by 0.67 plus tangent of 22 divided by, open parentheses, 1 minus tangent of 22 and so then I take the square root of that answer. And so basically you can just plug this in yourself. And I got 26.32 meters per second. Okay, so that's the fastest that you can drive this car with the bank. If you had this problem without the bank, I bet the speed would be smaller. The banks allow you to take the turns at much higher speeds. So I hope this made sense. I'll quickly review over this. We used the forces in the y direction and the forces in the x direction to write out our first expressions using Newton's second law. And then we set that equal to mv squared over r, the x component. Did some little algebra, moved some stuff around, and came up with this final expression that you could pretty much use anytime you have a question similar to this. Okay, I hope that helped. Feel like I kind of ran through it maybe a little too fast and I should have broken it down some more, but hopefully it made sense, and we'll see you on the next